What you'll notice is spanning tree convergence is very quick, and that's because we're running rapid PVST plus. I didn't make any changes on these switches from a spanning tree point of view. So the command show run pipe include span shows the default config. And notice the spanning tree used is rapid PVST. In the output it shows as RSTP or rapid spanning tree, but this is actually rapid per VLAN spanning tree. We can change the mode of spanning tree, but before I do that, just to make the point again, at the moment, show spanning tree on switch 3 shows that the root port is gigabit 01, this port. If I shut that port down and then type show spanning tree again, what you'll notice is gigabit 00 is the root port. Convergence is very quick with rapid spanning tree because it doesn't use timers. So the max age and forward delay timers are not used for convergence. The switches send messages to each other with rapid spanning tree to enable quick convergence. So now if we change the spanning tree type or mode to PVST, we should see that spanning tree takes a lot longer to converge. So I'll change that on all switches. Switch 3, switch 4, switch 5. So back on switch 3, show spanning tree. Notice we can see that the switch is still learning which ports are the root port, designated port, or blocking port. When in the learning state, traffic will be blocked. User traffic will only be forwarded when ports transition to the forwarding state. At the moment you can see that the spanning tree protocol used or shown here is IEEE, but once again you need to be careful because on Cisco switches, even though it displays IEEE, we're actually using PVST. PVST is once again backward compatible, so it will be able to talk to an 802.1d switch from another vendor as an example, so we can see IEEE in the output here. So once again, show spanning tree. The root port in this case is now gigabit 00. So what happened, because previously we had switch 1 as the root. It still has our command. Show spanning tree shows us that the switch is the root of the topology, but gigabit 01 is not shown in the output here because I need to no shut that port. So conf t interface gigabit 01, no shut, show spanning tree. Notice that port is a listening port. Gigabit 00 is a blocking port. So this port is blocking, this port is listening. And what you'll notice is it'll take it a while to converge. I'll put an IP address on the switch while we're waiting, and then I'll demonstrate this again. Put an IP address on switch 1. I'll no shut the interface. So ping 10.1.1.1. We can ping itself. Switch 3, no shut the interface. Ping 10.1.1.1. Ping succeeds, so I'll just do that again. Notice the ping from switch 3 to switch 1 succeeds. Show spanning tree. Convergence has taken place because gigabit 01 is the root port and is forwarding. But now if I shut down gigabit 01 and then try and ping switch 1, the port has gone down, but pings are failing even though we have a redundant link. Show spanning tree shows me that the root port is still learning. Still learning. Pings fail. PVST takes a long time to converge. It can take 30 seconds for that convergence to take place. As you can see there, it's just happened. Show spanning tree shows us now that gigabit 01 is forwarding. But once again, if I no shut gigabit 01 and did the ping again, the ping would fail because it now needs to learn that this is the better path. Show spanning tree. Notice the root port gigabit 01 is in the listening state. So we have listening, then we have learning, and after a while it should go to forwarding, but that can take 30 seconds. So it's still learning, now it's gone to forwarding, and now pings will succeed. So ports have different states. In a blocking state, user traffic is not forwarded. The switch doesn't learn MAC addresses based on frames received. This is a stable state for a port. A listening and learning port do not forward frames either. Listening ports don't learn MAC addresses based on frames received. In other words, they don't update the MAC address table. A learning port does update the MAC address table. This is a temporary state or transitionary state while the switches learn the topology. In a forwarding state, frames are forwarded, MAC addresses are learnt, and this is a stable state. In other words, this is not a transitionary state. This state will stay that way until there's a change in the topology. A disabled port doesn't receive frames, doesn't forward frames, doesn't learn about MAC addresses on a port, and this port will stay in that state until you enable the port. Now if we change that to rapid spanning tree, so spanning tree mode, rapid PVST, what we should notice is that convergence takes place a lot quicker. I'll only enable rapid spanning tree on switch 1, 2, and 3. Show spanning tree, or rather show spanning tree, shows us that the spanning tree mode now enabled is rapid per VLAN spanning tree. We've got a path cost using gigabit 01. So as you can see, gigabit 01 is the root port. The switch can ping switch 1. I'll shut that port down. And when we do a ping again, it instantly can ping switch 1, even though we've just seen the interface go down in the output here, because spanning tree converges a lot quicker when using a rapid spanning tree. So the moral of the story is that in the real world, you want to use a rapid PVST rather than PVST.